So hello friends, in today's video, we are going to discuss about the EDFA, Erbium Doped Fiber Amplifier. So we will discuss in detail about the EDFA, what is the EDFA, what is their advantage, what is EDFA's disadvantage, how the EDFA work, how many types of EDFA exist, what are their architecture, all these things we will discuss in detail about the EDFA. So let's start about Erbium Doped Fiber. So what is EDFA? Summary we can see here. An erbium doped fiber amplifier is a critical component in optical communication system. It plays a crucial role in amplifying signals transmitted through optical fibers. So basically what happens when the signal travels into the optical fiber, it is attenuated by some linear and non-linear effects and by some fiber impurities, etc. So whenever the signal is traversing from one end to another end, the signal is get attenuated. So EDFA is used to compensate all these losses at the end of the fiber sections. So EDFA has a very significantly contributed to the growth of transmission capacity, especially within the deployment of WDM systems. So let's see how they work. So their working principle at the heart of the EDFA technology lies in the erbium doped fiber. You can see here erbium doped fiber. This fiber is conventional silical fiber which is doped with the erbium ions, which is the main uh, use and principle of the EDFA. These erbium ions are strategically placed within the fiber to enable signal amplifications. EDFA utilize pump lasers to provide energy to the erbium ions. So this erbium ion is used to pump from lower energy level to the higher energy level, and we use the pump lasers to excite these erbium ions. So there are two types of pumping we use. 980 nanometer, when erbium is illuminated with the light energy at 980 nanometer pump, it gets excited to the long lifetime intermediate state. And alternatively, when we use the 1480 nanometer, erbium can directly excite it to a quasi-stable state using light energy at 1480 nanometer pumping. Stimulated emission, once in the quasi-stable state, erbium ions decay back to the ground state by emitting light within this frequency range. You can see 1525 to 1565 nanometer wavelength band. This decay process is known as the spontaneous process, but this decay process can be stimulated by pre-existing light, which is the incoming optical signals. So when incoming optical signal interact with the erbium ions, additional photons are emitted at the same wavelength with the same frequency direction of the incoming signal, and thus it is stimulated emission which helps to the amplification. We will discuss all these things in details with diagrams in further slides. The amplified signal emerged from the EDFA. What is EDFA summary? EDFA configuration. The basic configuration of EDFA include the following components: erbium doped fibers, pump lasers. Wavelength division multiplexing combines the signal via the pump wavelength so that they can propagate simultaneously to the EDF. In practice, EDFAs can be designed for different pump configurations: forward pumping, backward pumping, and bidirectional pumping. Forward pumping, the pump's energy propagated in the same direction as the signal. The pump energy propagates in the opposite direction of signal is called the backward pumping. And when we use forward pumping and backward pumping both together, this is called the bidirectional pumping. The most common configuration uses the 980 nanometer pump energy in the forward directions. Applications of EDFA. EDFA finds various applications in optical systems: booster amplifier, inline amplifier, and preamplifier. So before understanding about how the EDFA's work principle, their construction and their architecture, we just need to know about the some basic terminology, which is the spontaneous emission, stimulated emission, and population inversion. I have made a separate video between all of these, but let's see in shorts. What is spontaneous emission? When the lights automatically moves from higher energy state, or you can say the metastable state, to the lower energy state automatically without effect of any incoming photons or incoming optical signals. This is called the spontaneous emission. And during spontaneous emission, when the photon is emerged or emitted, and that photon is in very random with the respect of incoming photon signals. So you can say spontaneous emission does not help in amplification, but spontaneous emission creates to generate the noise, and this is the main cause of noise in the amplification. If an atom in the excited state, it may spontaneously decay to the lower energy level after some time, releasing energy from a photon, which is emitted in the random direction, and this is called the spontaneous emission. So you can see here, spontaneous emission takes place without interaction with other photons. If the spontaneous emission happens in a gain medium such as alpha, this spontaneous emission can be amplified by the process of stimulated emission and known as the amplified spontaneous emission ASA, which is the main cause of noise in alpha. So stimulated emission, you can see here, this is the, you can see these are the structure of an atoms. This is the nucleus. These are the different energy levels. These are the electrons moving around the nucleus. So the energy of an electron orbiting an atom nucleus is larger for orbits further from the nucleus of an atom. So let's understand the stimulated emission. What happens when an electron is excited from a lower to a higher energy level? It is unlikely for it to stay away forever. It means, let's understand this by the diagram. This is the energy levels. You can see here. This is the lower energy level. This is the higher energy level. So when the electrons move from lower energy level to higher energy level, the electron does not want to move forever in the higher energy level because every system wants to in the stable state. So what happens? The electrons move from higher energy level to the lower energy level by emitting some electrons, which is called the spontaneous emission. So when these electrons in the higher energy level is interact with an incident photons, then it will generate a photon which is identical with the incident photon in the terms of frequency, direction, and energy. So these immediate photons can have the amplification. And this is called the stimulated emission. It means when the electron in the higher energy level is stimulated or triggered by an incoming incident photons and to force or from moving from higher energy level to lower energy level, then this is called the stimulated emissions. So let's discuss about the population inversion. So normally a system of n atoms is in temperature equilibrium, and there are always more atoms in low energy state than the higher ones. But what happens when there is a lot of energy, lot of photons or electrons in the higher energy level than the lower energy level? So this situation is called the population inversion, and which is very important for the amplification process. Although absorption and emission is in energy is a continuous process, the statistical distribution of atom in the various energy state in the constant. I have made a separate video of the population inversion details. You can go to understand about the population inversion. Here in shorts, I just want to let you know to aware about the population inversion, what this is meaning. So if there are more atoms in the upper energy level N2 than in lower energy level N1, the system is not in thermal equilibrium. A situation not at equilibrium must be created by adding energy via process known as pumping. So normally there is higher electrons in the lower energy level than N2. But when we use some pumping or some extra energy from the external sources given to the electrons in the lower energy state, it moves from N1 to N2. And when the number of electron in N2 is more than the N1, this system is called the population inversion. So this is known as the population division, which is given by delta is equal to N2 minus N1. Light is amplified when the population inversion is positive. So when delta is positive means N2 is greater than N1, then this is called the population inversion. You can see here, this is like this is the three energy stream where we are using the 980 nanometer pump. You can see the electrons is moving from lower energy to higher energy state, and immediate is transfer from higher energy to lower energy. Fast radiating, you can see 1 microsecond is the state time here. Spontaneous emission you can happen. This is a random. This is a 1480 nanometer photons, and the electrons directly move to the metastable state. You can see here when the incident photon coming and interact with the electrons in the higher energy level, or you can see the quasi-stable, intermediate stable. The stimulated emission happens, and one new photons with the same direction, frequency, and phase with the incident photons generated and helps in amplification. So let's see what is EDFA co-directional pumping. So let's see the structure of like EDFA co-direction pump. You can see this is the out optical input signal. This is the direction of signal. This is the transmission fiber. So in transmission fiber, the signal is transmitted. This is the optical signal moving from this direction to this direction. You can see from left to right. This is the EDFA. You can see here. This is the input port. There is a tap. You can see here. This is the WDM isolator and filters. So what is the function of this isolator and filter? This isolator is used to combine the optical signals and the pumping signals. And isolator is used to prevent the signal propagation in the reverse directions. You can see this is the WDM coupler. This is the isolator and filter. And this is the WDM coupler. Sorry, this isolator, not this WDM coupler, which is used to combine the direction of signals and pumping signal. Now you can see the co-pump laser, 980 nanometer or 1480 nanometer pump. So this is the coupler which is used to combine this incoming optical signals and laser pump. Now these both signals are combined and go to the EDFA. This is the Eribium Dopped fibers. You can see again there is isolator and filter. This is a tap and this is the out signals. This is the transmission fiber. This is the direction of the signal. This is the amplified output signal. You can see this is the signal input signal, which is low intensity, and this is the output signal, which is higher in intensity. So this is co-directional pumping. Let's see the counter direction pump. This is the optical input signal. This is the direction of signal. Transmission fiber, again same. This is the input signal. Tap, there is a WDM isolator filters. This is a splice. This is the alpha direction. You can see the signal is moving from left to right. And here there is a WDM coupler. This is a counter pump laser because this pump laser is in the opposite direction of the flowing or the direction of the signal. That's why this is called the counter direction pump. So this is the WDM isolator and filters. This is tap and this is the out signal. And you can see this is the transmission fiber. This is direction of signal. This is the amplified signal. So what happening? The weak incident signal is coming here combined with the pump lasers and the signal is amplified. You can see here. This is also known as the preamplifier. Why? Because the amplifier is in near to the receive direction. That was it is called the, you can see, the preamplifier. Booster amplifier you have seen in the previous, which is counter co-direction pumping. So dual pump, you can see this is the optical signal. This is direction of signal and transmission fibers. The signal is going inside. Here the WDM isolator and filter. Here this is the WDM coupler. Here you can see there is the laser pump. This is erbium doped fibers. Here you can see this is the counter pump laser. So you can see we are using the laser pump or in both the direction, in the direction of the signal and in the reverse direction of the signal. So this is called the dual pumping. Out, transmission fiber, direction of signal, and you can see this is the amplified signals. So what is the amplified spontaneous emission? SC noise we already discussed. Like what happens when, you can see this is the spontaneous emission. When this spontaneous emission happens in the gain medium are subsequently amplified by stimulated emission. These spontaneously emitted photons travel along the amplifier length and are amplified during the entire main laser pulse. And this AC can reduce the population inversion as well, because what happens in population inversion, many of electrons lost during the spontaneous emissions. So in summary, ASC is an inherent phenomenon in laser subsystem, and understanding its effect is crucial for designing efficient high performance laser. You can see this is the amplification mechanism. This is the population inversion. This is the amplification mechanism we have already discussed. You can see electrons absorb the energy, go to the higher energy level, decay, rescend, decay fastly to the metastable state, and when it automatically decay from higher energy metastable state to the lower energy state, it is random in direction. It is called the spontaneous emission. And when these electrons are when we are using 1480 nanometer, while it is going to N3 level, it directly go to the metastable state. And what happens when the incoming photon signal is interacting with this higher energy level? Then this is called the stimulated emission. So let's see the amplification mechanism when we are using 980 nanometer laser pumping. You can see when we are using 980 laser pumping, there are three energy level, N1, N2, N3. The energy absorbs the 980 nanometer photon signals, go to the N3. Here it moves only for you can see 1 microsecond and moves from N3 to N2 very fast. And this is, you can see that this is the non-radiative emissions. And here is the metastable state. So when the electrons fastly absorb the energy, move to the N3 fastly from N3 to N2, and here it is stay for 1 millisecond. So here the electrons are get populated, and when this electron from this N2 energy levels moves automatically, it emitted a photon which is in random direction. This is called the spontaneous emissions. And when these electrons is interacted by the incoming photon signal, this is called the stimulated emission, and it generates the same photon, or it generates the photon which is identical with its energy, phase, and directions. So this is the amplification mechanism. The difference between 980 nanometer and 1480 nanometer is that the 980 nanometer frequency has three energy level and 1480 has only two. We will discuss amplification mechanism. You can see when we are using 1480 nanometer. So here when we are using 1480 nanometer, the electrons absorb the energy and move to the N2. There is only two energy level. So there is no any population inversion happens in this 1480. I have made a separate video with for 980 and 1480 nanometer. You can go there to understand in details. Here I have just explaining in very short. Like when the electrons move automatically from N2 to N1, it generates the photons which is in random direction. This is called the spontaneous emission. And when these electrons interact with the incoming photon signals, they and generate the electrons which is used for amplification. So let's see for booster, pre and inline amplifier. So booster amplifier, you can see this is the transmitter. Pump laser. Pump laser is goes to the coupler. Lambda P. This lambda P is a laser photon. This is the transmitter. You can see this is the transmitter which generates the signal, transmitted signal. These two signals are coupled and goes to the erbium EDF. This is called the lambda signal power. These are transmission optical signals. You can see this is the receiver. So basically booster amplifier, it means when the alpha amplification is at the transmitter side, it is called a booster amplifier. Inline amplifier, you can see this is the lambda signal. This is a transmission optical fiber, and here the pump laser is in between the fiber span. So here it is called the inline amplifier. Here is the transmission optical fiber, here is the transmitter optical fiber, and alpha is used in between this transmitter and receiver. That's why it's called the inline amplifier. When this alpha is at the starting of the transmitter, it's called the booster amplifier. Preamplifier, you can see this is a transmitted signal. This is the optical fiber. This is a delta S. You can see pump laser is used at the receiver side. This is the alpha which is used at the receiver side. So the alpha system is used at the receiver side. So it is called the preamplifier. So this is about booster, pre and inline amplifier. So let's see about alpha key optical characteristics. So saturated optical power, or simply maximum output power. Saturated output power is the maximum output power from an amplifier when sufficient signal input power is launched to the amplifier. A booster amplifier typically operates under this condition, and thus saturated optical power is an important characteristic of a booster amplifier. A small signal gain. A small signal gain is a gain in an amplifier when the signal power launched to the amplifier at very small, typically around minus 30 dBm. A pre-amplifier typically operates under these conditions, and thus small gain signal gain is an important characteristic of a pre-amplifier. So here you can see the saturated optical power is the main characteristics of the booster amplifier. A small signal gain is the main characteristic of the pre-amplifier. Noise figure. Amplification by an EDFA adds some noise to the original system because of AC noise, which we have already discussed, mainly due to amplified spontaneous emission (ASA) from the EDF, and thus decrease the signal to noise ratio. Noise figure of an optical amplifier is a measure of degradation in the signal to noise ratio. It means noise figure calculates or it gives you the at calculation when a signal is passed through any amplifier, how much it will degrade when it comes from the output. The signal to ratio, how much the signal to noise ratio will degrade after passing through an amplifier. So this can be calculated by the noise figure, and this is expressed in a dB. And a lower noise figure indicates a lower noise characteristics, therefore minimum is 3 dB. In general, ASC grows fast when the signal input power is low. Thus, noise figure is an important characteristic for a preamplifier, small input power. On the other hand, ASC is well suppressed when the signal input power is high, and the noise figure value measured at a high input power has a little importance. At typically noise figure values of commercial alpha at a small signal input power is within the range of 5 to 7 dB. So gain flatness, when an alpha is used for wavelength division multiplexing transmission, it would be ideal that for all WDM channels have equal gain, because the input of the alpha is multiple channels. I mean this that the you can see the aggregate signal is going to the alpha. So it is very important that all the channels have the equal gain. That is called the gain flatness. In reality, however, each of the channel has a different gain value and the variation referred to as the gain flatness. Gain flatness is particularly important when many alphas are concatenated in an optical transmission line, submarine or optical transmission, as the given variation is accumulated in the alpha chains and results in larger signal power difference between the WDM signals. So here the mean aim of this gain flatness is when we are using the alpha in concatenated means one alpha then another alpha then third alpha and four alpha. So what happens, the difference in the gain of the all the channels, the difference in the gain of the channels is getting bigger and bigger when we it is passing through multiple amplifiers. So it is very important characteristics. Gain flatness can be improved by, for example, modification of glass composition of EDF or the incorporation of external gain flattening optical filters. The power conversion efficiency and gain. The input and the output power of an EDFA can be expressed as P out is less than or equal to P in plus lambda P upon lambda as PP in. Maximum output power depends on a wavelength review of pump to the signals. Pumping works only when lambda P is less than lambda S. Means lambda S is greater than lambda P. And for appropriate gain, P S in should be less than PP in. The power conversion efficiency is defined as always less than unity. It is equal to 1 when all pump photons are converted to the signal photons. PSC is less than or equal to lambda P by lambda S is less than or equal to 1. Relation in input signal power and gain. We can write the gain amplification mechanism below. You can see this is the formula where input signal power is very large. PS in is very large, lambda P upon lambda S into PP in. The maximum G is unity. In order to achieve a maximum gain, the input signal power cannot exceed a value by this one. PS out is equal to signal output power. You can see here PS out is equal to signal output power, PS in is equal to signal input power, PP in is equal to pump input power, lambda P is equal to pump wavelength, lambda S is equal to signal of wavelength, and G is equal to gain of the amplifier. So let's discuss about some advantage and disadvantage. Characteristics of advanced advantage: higher pump transfer efficiency from pump to signal power, less greater than equal to 50%. Power transfer efficiency, wide spectral band amplification with relative flat gain greater than 20 dB useful for WDM application. Saturation output greater than 1 milliwatt 10 to 25 dBm. gain time constant long to overcome you can see patterning effect and intermodulation distortion, low noise, large dynamic range, low noise figure, polarization independent, suitable for long haul applications. So disadvantage of ADVA, relatively large devices, not easily integrated with other devices. SA, amplified spontaneous emission. This there is always some output even with no signal input due to some extinction of ions in the fiber. Spontaneous noise is always there in the alpha. So this property, this AC amplified spontaneous noise limits the number of alphas in the fiber spans. Crosstalk effect, gain saturation effect, pump laser necessary. Need to use a gain equalizer for multi-stage amplification. Difficult to integrate with other components. Dropping channels can give rise to error in surviving channels. So these are the advantage and some advantage and disadvantage of the ad. So let's see 980 nanometer versus 1480 nanometer pump alpha difference. So you can see here 980 nanometer pump gives less noise. Unlike 1480 nanometer, 980 nanometer pump cannot stimulate back transition to the ground state. You can see here this is some property difference between 980 nanometer and 1480. The main difference between 980 nanometer and 14 nanometer is 980 nanometer has a 3 energy level diagram and 1480 has a 2 level. So when we are using 1480, the electrons jump directly from lower state to ground state to the metastable state. You can see some difference. I have made a separate video in detail, so you can go there to understand. So here in short, I have details. You can see the shorter wavelength results less noise. 980 nanometer pump needs less electrical power. 980 nanometer pumping results in a noise figure 1 dB lower than that for 1480 nanometer pumping. Wasted energy because electron must relax unprotectively. Higher G, narrow absorbed band. The same way you can see 1480 nanometer pumping gives higher noise. 14 nanometer pumps can excite the ions directly to the metastable state. And the inversion factor of 1480 nanometer pumping for the best one to get is 1.6. Here are some you can see and the screens, some difference. Need higher drive current, high dissipation required, expensive, smaller G and larger tolerance in pump availability. So let's see pump power versus gain graph. You can see here this is the pump power and this is the gain. So when we are using the pump power 2 milliwatt, 4 milliwatt, 6 milliwatt, 8 milliwatt, 10 milliwatt. So when we are using, you can see when we are using 2 milliwatt and we are using the length of 5 meter, you can see the gain is like this. When we are using 4 milliwatt pump power and 10 meter length of the fiber, you can see the gain is like this. So you can see when we are increasing the pump power and length of the fiber, the gain is also increasing. So this is about the pump power and gain graph. See alpha gain and wavelength graph. You can see here, this is the wavelength 1530, 1534, 1550, 1560 nanometer. This is the gain. This is the pump power. A pump power, B pump power, C. You can see pump power C is greater than pump power B is greater than pump power A. So when we are using pump power A, or you can see the brown one, you can see the graph is like this. When we are using higher pump power than pump power A, you can see the graph becomes like this. When we are using much higher power than A and B, it becomes this. So when the power is increasing, you can see the gain is also increasing, but it's also within a limit. You can see by this graph. It's all about that for working principle and all these things. Thanks for watching.